Day 20, page 622, number 27. This is probably best done thinking about a parallel plate situation. Once again, these parallel plates are they're two-dimensional surfaces, usually rectangular, but this is like the bird's eye view. It's kind of like they're two walls of a room. You have the west wall of a room that's a big flat surface, and the east wall of a room, in this case the negatively charged plate, is a negatively charged surface. And I know this has to be the case because it says somebody has to hold that particle in there, that negative 20 nanocoulomb charge, and it says it's a very small conducting sphere. The reason why they usually say that is because we don't want the sphere itself, the negative 20 nanocoulomb sphere, the charge there, to be messing with the field. In other words, the field controls that little charge. The little charge doesn't really change the field. It's kind of like saying, I know that all people have a gravitational field. We all have gravitational fields, and the Earth has a gravitational field, but basically my gravitational field has little effect on the Earth's gravitational field. The Earth's gravitational field right near me is still it's very uniform, straight down. I don't really change the gravitational field of the Earth per se, even though the interaction between our two fields is what essentially causes the force between us. But the Earth's gravitational field would still be drawn uniformly towards the center of the Earth. Same thing here. This little charge's electric field doesn't change the electric field of these two parallel plates. And in general, or specific, the parallel plates always have an electric field, by definition, from positive to negative. So if we were to draw it, it would look like this: uniform, equally spaced, and the negative 20 nanocoulomb charge, it wouldn't matter where I put the negative 20 nanocoulomb charge, dead center, towards the left, towards the right, it would still have the same force everywhere in that field. And when you have these parallel plate problems, almost always you will start off, or at least some point in time, be using the equation E equals F over Q, or F equals EQ, because you will have a uniform force causing uniform acceleration for that particle if you allow it to move. Once again, do not use any of the point particle equations, like F equals KQQ over R squared, or E equals KQ over R squared. Do not use any of those point particle equations for these parallel plate problems. And the other thing, directionally, it says when you lower this little charge in there, somebody's holding onto it, or a force gauge is holding onto it, and we have to hold it with a force to the right. Somebody is holding it with a force this way. This is the force we're applying. Because the field itself, I'm going to call that F sub 1, and it's a force of 2 nanocoulombs. That's a force towards the east, because the conventional direction is towards the east. So I'm holding this particle with a force towards the east because the field wants to force the particle this way, which is opposite the field, because the electric field is always defined in terms of which way the force would act on a positive particle, but this is a little negative particle, so the field, which is always drawn from positive to negative, as you can see in my diagram, always acts oppositely on a negative charge. The negative charge is repelled by the negative plate, so the electric field is exerting a force towards the west on this charge, and our force is towards the east. But bottom line, once again, we are given Q, and we're given F, so you're just going to calculate E, but what they also want you to say is the direction of the E field, which is towards the east. So you're going to plug in the two numbers, calculate the magnitude of E, and say that the E field, electric field strength, is towards the east.